All right, so here what we're going to do is use the properties of summations that we found in the previous video, at the end of that video, to evaluate this integral. Okay, now this integral, the integral from 0 to 2 of 2x minus x cubed dx, I'm going to use the definition of the integral using my my limit of a Riemann sum idea, and we're going to use right endpoints because that's going to give us the easiest time here. So this is equal to the limit as n goes to infinity of the sum from I equals 1 to n of, now it's f of xi, right? And in order to find xi, I first need to know what delta x is. So let me leave this alone for a second. Come over here. What is delta x equal to? Well, remember delta x is equal to b minus a over n. 2 minus 0 over n. And this time we're letting n be just an n. We're not assigning a value to it because we want to be able to take a limit as n goes to infinity. So this is equal to 2 over n. What is xi equal to for just any generic I? Well, remember, we came up with this in section 5.1. xi is equal to a plus delta xi. A being the left endpoint of the interval I'm integrating over. Well, a is equal to 0. And I'm not going to bother writing 0 plus something. So xi is equal to delta x times I, or 2I over n. If this is my f of x right here, then what does f of xi look like? Well, it would look like 2 times 2I over n. I'm plugging this xi in for the x right here, minus 2I over n cubed, because it's minus x cubed over here. Let's write that in simpler notation, or simplified. So this would actually be the same thing as 4I over n minus 8I cubed over n cubed. Okay? So that f of xi, if I'm using my right endpoint method, I don't need to put a star up there. It would look like this. 4I over n minus 8I cubed over n cubed. And then I need to multiply by delta x, which is equal to 2 over n. Okay? So this is like my f of xi, and this is my delta x right there. Okay? Here's where I want to use properties of summations. So first I'm going to distribute the 2 over n into this guy. Okay, so that's going to make this look like 2 times 4i, which is 8i. N times n is n squared. And then I'm going to have minus 16i cubed over n to the 4th. Okay? Now, one of my properties of the integral, of the summation down here, said that if I have a sum of a formula involving a difference, I can split it up into a difference of those two sums. In this case, that's going to look like this. The limit as n goes to infinity of the sum from I equals 1 to n of 8i over n squared minus the sum from I equals 1 to n of 16i cubed over n to the 4th. Okay? Now what I can also do is use this first property of sums, so property 9 is what we're calling it here, to pull any constants out of those summation symbols. Now the n here, as far as the summation is concerned, is a constant. It's being treated like a constant. The limit will treat it as a variable because we're allowing n to go to infinity. But each sum, the only thing that's thought of as a variable is that I. So anything that doesn't involve an I can be brought out of the summation symbol, still kept within the limit though. So this is equal to the limit as n goes to infinity of 8 over n squared times the sum from I equals 1 to n. The I is all that's left there. Minus, I can bring a 16 over n to the fourth out. Times the sum from I equals 1 to n, and an I cubed is all that's left in there. The idea here is that the summations that are left are sums of powers of I, sum of the first powers of I. This is the sum of the first n cubes. So those individual summations there, we have formulas for those here and here, which can replace those summations, okay? And they look like this. This is equal to the limit as n goes to infinity of 8 over n squared. This sum, the formula on the previous page, looked like n times n plus 1 over 2. And then I have minus 16 over n to the fourth times the sum of the first n cubes looks exactly like this thing, but squared. Okay, now comes a whole bunch of simplifying. So first of all, this n can cancel with one of those n's. This 2 and this 8 will do some canceling. I'm left with a 4 there. Let's bring the, let's square this stuff. So this is equal to the limit as n goes to infinity of what's left here? 4 over n times n plus 1. So that's going to look like 4 times n plus 1 over n, like that. Over here, I'm going to have minus 16 over n to the fourth. Squaring everything in here is going to look like n squared times n plus 1 squared over 4. Okay, and then there's more canceling that can happen. The 4 and the 16, that becomes a 4. Cancel the n squared with 2 of the n's there. That leaves me with an n squared there. And now let's look. I have a 4 in this term, and I'm left with a 4 in that term. I can bring the 4 completely outside of the limit because we have that property of limits. What does that leave me with? N plus 1 over n, which can be split into two fractions, n over n plus 1 over n. And the n over n simplifies to just 1. So I have 1 plus 1 over n. What about this? What am I left with? Well, I eliminated that 4, and now what I have is n plus 1 squared over n squared, which can also be written this way. That's the same thing, okay? My reasoning for doing that is because now I can do this. The limit as n goes to infinity of 1 plus 1 over n plus, once again, the n plus 1 over n can be written as 1 plus 1 over n. That's being squared. Having written everything out this way, when I take the limit as n goes to infinity, oh, sorry, this is, I've been putting a plus where I should have been putting a minus. That should be a minus. These terms are going to go to 0 as soon as I apply that limit. So that means that what's left in here is 1 minus 1, which is 0. And that tells me that the integral is equal to 0. Okay? Now this is the first time we've had an integral come out to 0, but think about what that would mean in the context of how we defined the net area in this section. So if you come up here and look at the function that we're integrating, go graph this in a graphing calculator or Desmos or something, 2x minus x cubed. And then look at the interval from 0 to 2. Some of that area will come out positive and some of it will come out negative. And it turns out that the area of the positive part and the area of the negative part are exactly equal to each other, at least in absolute value. So their net area comes out to 0. They cancel each other out completely. Okay? It's not immediately obvious that that's the case just by looking at the graph, but this establishes it for a fact. Okay? So obviously this is a ton of work for an integral of a function that's not even that complicated. And thankfully, once we get through section 5.3, we'll be able to evaluate integrals like this in a tiny fraction of the amount of time that it took us here. This is what we call evaluating an integral from first principles. And what that means is we're using the definition of the integral directly to do it. But in section 5.3, we'll introduce something called the fundamental theorem of calculus, which gives you a much, much faster technique that doesn't rely on the definition of the integral. Instead, it relies on a theorem about the integral to evaluate these much more quickly. Okay? But fortunately, even without the fundamental theorem of calculus, there are some integrals that can be evaluated without having to use the limit definition of the definite integral. And the reason for that is because we're talking about areas. In some cases, the area under the curve that we're looking at, over whatever interval we're looking at, exactly matches a geometric shape whose area formula we already know. So in some cases, you can use a geometric area formula in place of the limit definition. Here is one such example. I'm looking for the integral from -3 to 3 of the square root of 9 minus x squared dx. Now, if you were going to use the fundamental theorem of calculus to evaluate this, which again, that's in section 5.3, we haven't talked about it, you need more techniques in order to do this. In fact, the technique that is required to evaluate this integral without a geometric formula isn't covered until a little ways into calculus 2. It involves something called a trigonometric substitution, and we're not doing that in this class. However, if you were to graph the function y equals 9 minus x squared, you get this, -3 to 3. That's the function y equals the square root of 9 minus x squared. We've dealt with functions of this form before, so this shouldn't be a surprise. It's a semicircle. It's a semicircle with a radius of 3. So rather than try to deal with the limit definition of here, just think of what the area of a semicircle of radius 3 would be using geometry. This, 9 minus x squared. Area of a circle is pi r squared, so pi times 3 squared. A semicircle would be half of that. Okay, so this is equal to 9 over 2 times pi, or 9 pi over 2. Notice that was way, way easier than it looked initially, especially following that previous example. It's just we don't very frequently get to use these formulas, so we want to take advantage of them when we can. Here's another example. I want to evaluate the integral from -2 to 4 of this linear function, 2x minus 1. This one wouldn't be terrible to do using the limit definition, but we don't actually need it if I graph that function. Think about that for a moment. What does this graph look like? We want to go from -2 to 4. This is a function that's linear. It has a slope of 2, a y-intercept of -1. And I'm not going to draw this very accurately, but it's going to look something like that, right? So I have some negative area and I have some positive area here. But notice that both areas, both regions look like right triangles. And I have area formulas for triangles that are easy enough to find. So all I need is the base and height of each of these triangles. Now notice here, the base of this triangle, let's do this. I'm not doing that very well. Is this value here, whatever that comes out to be. The base of this triangle is right there. In order to determine what the base is, I need to know what the y-intercept of this function, or the x-intercept of this function is. Y equals 2x minus 1. Finding that x-intercept is easy. You just set y equal to 0, which implies that x is equal to 1/2. So that right there is 1/2. What then is the base of this triangle? Well, it's I have a base of 2 here, plus an additional 1/2 here. That would be 2.5, or 5/2. And then this guy right here, from 0 to 4, let's go like this. That's 1/2 right there. Or from 1/2 to 4 is the same thing as 3.5, or 7/2. Okay, so the base of this triangle is 5/2. The base of this one is 7/2. What about the heights of these triangles? What are the heights of these triangles? The height of this one I can find by finding the y-coordinate of this point. I just need to plug a 4 into my function. 2 times 4 minus 1 is 7. Same thing here. Plug negative 2 into this guy. The negative 2 plugged into this is going to give me negative 4 minus 1, which is negative 5. Okay? So now, if I think of that as negative, that's what's going to give me a negative area here. How do you find the area of a triangle? Well, this first triangle, it's going to be, let's do this, negative 2 to 4 of 2x minus 1 dx is going to equal 1/2 base times height. 1/2 times 5 halves times negative 5. Plus the area of this triangle right here, which is 1/2 times base, which is 7 halves, times height, which is 7. Okay, this is going to be equal to negative 25 plus 49 over 4, which is equal to negative 24, or no, sorry, positive 24 over 4, or just 6. Okay? So we're going to end up with an area, a total area of 6 here. And notice I'm just using geometric formulas to determine that. Areas of triangles and then adding the results. Careful to make this triangle a negative area because it's below the x-axis. Okay? All right. So even though we've actually been able to evaluate a few integrals exactly, until we get to section 5.3, most definite integrals are going to be beyond our reach. And that's because we're relying on techniques that we don't get to use that often in practice, one of which is geometric area formulas, the other of which is these summation formulas that we introduced. A lot of functions won't be able to be integrated using those techniques. So until we get a better technique, we're still pretty reliant on approximations. Now we've done left endpoints and right endpoints when we've done these rectangular approximation methods. And what we saw is that in a lot of cases, you're overestimating or underestimating by a fairly significant amount if you're not using enough rectangles. So there is an alternative to the left endpoint and right endpoint, and that's the midpoint rule. The midpoint rule is basically just evaluating the integral or approximating the integral using a Riemann sum whose sample points are specifically chosen to be the midpoints of each subinterval. So for example, we have this function right here. We're not told what this function is, but if you look at the rectangles, the heights of these rectangles appear to be determined by whatever point is exactly in the middle of each subinterval. Now, the benefit of choosing the midpoint can be kind of seen from some of these rectangles. Notice, for example, this first rectangle. Half of the rectangle appears to underestimate the area under the curve because we have this excess here. But then the other half of the rectangle overestimates by a little bit because we have this excess in the rectangle. So what the midpoint rule is doing is it's creating rectangles that sort of compensate in a way where part of the rectangle is an underestimate and part of the rectangle is an overestimate, and so there's some canceling of that error that happens there. You can see that a little more clearly in these last three rectangles. For example, right here, this rectangle has a big underestimate right here, but then a relatively big overestimate, and these are partially canceling each other out. They don't completely cancel each other out because this area is not exactly equal to that, but you can see just from this image that it's fairly close. So the midpoint rule tends to give us very accurate approximations without needing too many rectangles in the approximation itself, okay? And this little formula right here tells you how to find the midpoint of an interval. You add the endpoints and then you divide by 2. But most of the time you can tell what the midpoint is just by looking at the numbers. You usually don't even need to bother with a formula. So here's an example where we want to use the midpoint rule. We cannot evaluate this integral using the techniques we've talked about. Instead, we're going to approximate. It's the integral from 0 to 4 of 1 over x squared plus 1 dx, and we're using the midpoint rule with n equals 4 rectangles. Okay, so to do this, where's my notes that I had taken? There we go. What we're going to do is start by looking at the interval from 0 to 4. Okay, and I'm splitting this up into 4 rectangles. If I split it up into 4 subintervals, I'm going to have the interval from 0 to 1, 1 to 2, 2 to 3, and so on and so forth. What I want is the midpoint of each of these subintervals. Midpoints. I could use the formula, but it's easy enough to tell what they are. That's 0.5, 1.5, 2.5, and 3.5. Okay? So how then do I find this approximation using the midpoint rule? So according to the midpoint rule, my integral from 0 to 4 of my function, I'm going to call this f of x for a second, f of x dx is approximately equal to the sum from I equals 1 to 4, in this case, of f of xi bar. The bar is the notation that we're using for the midpoint of an interval. Xi bar delta x. What is delta x in this case? Well, delta x is equal to 4 minus 0 over n, which is also 4. So it's equal to 1. Okay? Now, f of xi star. So these are my xi bars. This is x1 bar, x2 bar, x3 bar, x4 bar. 0.5, 1.5, 2.5, 3.5. This is equal to f of 0.5, so 1 over 0.5 squared plus 1 times delta x, which is 1, plus 1 over 1.5 squared plus 1 times 1, plus 1 over 2.5 squared plus 1 times 1. You don't really need to write the times ones in here, but I'm just doing that so you're not looking at this later and thinking, where did the delta x go? Plus 1 over 3.5 squared plus 1. And again, use a calculator here. This comes out to approximately 1.321. Okay? So that's what we call the midpoint rule. All right. I think I'm going to do the rest of this section in a part 3.